So I like to speak Edwin van der Heijden from TNO.
Hi, good afternoon everybody. I'm Edwin van der Heijden. I will give a presentation on our activities on additive manufacturing. I'm working on a department at TNO that develops additive manufacturing equipment, and we're focusing mostly on polymer printing. But I will show also some other activities in this field. So to give you an overview of my presentation, at first we have an initiative which we're collaborating with the Technical University in Eindhoven. We call it AM Systems Center. I will come back on that. And for AM it's important also to keep the application in mind, and I will give you an application for additive manufacturing that we look at the moment, and that is automotive polymer spare parts printing. Why we think this is a good proposition, I will give you some details on that. An important aspect is to meet the requirements for these spare parts is like cost, of course. And I will give you our roadmap on what we do on reducing this cost. And a second part is, of course, the quality has to be meeting the demands. But we have to see how far I get. So I won't try to rush. So I'd rather say the first part correct than really go into the quality control. But we'll see. So starting with this initiative, we as TNO are more on the applied research. And Technical University is working a lot with PhDs and postdocs, and together we have a broader proposition that we can make. So for the early research we can put PhDs on the topic, and later we get more involved as TNO making it applied. I will focus in my presentation really on this industrial polymer printing, but we also work, we have 4 programs actually. One is food printing. I actually did a project with Barilla on pasta printing in the past. We also do printed electronics. That's also really a new step, like integrating electronics during printing. So not like one material, but integrated electronics. Pharma printing, you can imagine that you can customize medicines on personal needs. Ceramics printing for high-tech. And that's it. So to tell you more about our platforms, fuse deposition modeling, we're not into polymer fuse deposition modeling, but more on food printing with FDM. Also we have a strong background in stereolithography, and we see it as the axis of the quality. We can have very precise details with this SLA technology. But we also have a part that's working on selective laser sintering. I don't know if this terminology is known. I at least will explain selective laser sintering more in detail. Otherwise I think it will, it's too important for the story. And there we mostly work on throughput. But in the end we want both to come together. We want any good quality and the good cost price. And that is the next generation Print Valley 2020 which we're working on. So to tell a little bit more on the application we foresee, and that is automotive polymer spare parts. And of course, the cost is an important topic, and I think it is very hard to beat for large quantities with injection molding. But I also went to these warehouses where a lot of spare parts are stored for years. And even not all of them are sold, some are scrapped. And if you take all this cost together, then we believe that AM could be an option by printing on demand. But as saying printing on demand, you cannot say, okay, you have to wait for a week for your spare parts. So we aim for 24 hours delivery there. And also for automotive, it has to be the same quality as the original part. And of course, this is really broad. This is still a lot of topics. And where we want to focus first on is under the hood parts. And there already PA6 nylon parts are used a lot. They high temperature resistance. And PA6 is a material that you can do with selective laser sintering. How do we think we can realize this? And The process at now is, it takes quite a long time, more than 24 hours sometimes, the printing, and even then it takes a lot of labor to come to this product. So we're aiming for a high-speed printer and also automate some of the post-processes. And also by printing faster, we are aiming at this 24 hours that we can deliver, so you have not the parts stored all the time, but you print on demand. And the idea is that you have regional hubs and that you print it at the region where you need the parts. Of course, this is still not reality. So to look at the chain now, you see a spare part, and you see these big warehouses in the middle, and then in the end you have the automotive transportation system. What we then foresee is that you print it on demand, and to make it cost competitive, for injection molding, making it on demand is not an option. Like do the injection mold for one part is not very cost efficient. But for AM, it is. It doesn't make a lot of difference in cost if you make 1 or 10 parts. So what you typically see is that up till a certain number, AM could be attractive. And now we position it to 1,000 to 10,000 parts. I think it's already quite high. And of course also the complexity. With AM you can make very complex parts, even parts that you not do with injection molding. And that aspect you see also for metal printing as an important one. To go to our proposition to reduce this cost per part. So what is the idea? So if I go to selective laser sintering, the steps are coating a layer of powder, polymer powder, it's typically PA12, but it can also be PA6. Then preheat it, and then selectively sinter the powder particles together, and then go to the next layer, as you saw with the animation. But typically these 3 steps are done in series. So each recoating, preheating, sintering. And of course you can make these process steps quicker. And then, for example, if you make the process steps 3.3 times quicker, the process is 3.3 times faster, as you can see here. But what we work on is not like having one build chamber and moving with your processes over the build platform, but have your processes fixed and move your build platform from one to the other processes. And what you see here is these 3 process steps next to each other. And then we have 3 build chambers in this example. And the build chambers are moved from one process station to the other. So if you have the same processing speed, you already have 3 times the throughput, because in the same time you have 3 build boxes that are manufactured. But now, if I now make my process more fast, like 3.3 times faster, then the throughput gain is 3 times 3.3, so then you have an increase of 10 times. So then, that makes a much bigger step. Then on the automation part and this labor part, what you typically see now, there are a lot of standalone machines. I already see on the form next some steps like that you can have a robot picking out the build box, maybe going with AGVs too, that could be, but typically then you have a lot of these machines and you have to handle all these build boxes. Our vision is more to go towards like these build boxes moving all the time with a lot of process stations, and we think that this automation of this system would be more easy. To do some benchmark, and the benchmark, how do you compare these different systems? We do that with how many liter per hour product you can produce. And for example, this new system, the EOS P500, they have in the brochure that they can produce 6.6 liter per hour. And the other system, they all, and also, and if you look at the Print Valley, then you can, with the same process, make this almost factor of 3. So then you can make a big step in this throughput. And even that is the carousel. And if we speed up the processes, you don't have this 3.3 gain, but a factor of 10. So you really see like that 42 liters per hour becomes realistic. So that's a big step. So why bother about these liters per hour? And the cost of your product is a sum of the material cost, the labor cost, and machining cost. And we put this in this graph. This one is like the machining, like how fast is the throughput, and the other one is the cost of the product. And so with these pie charts, the build-up of the cost is shown. So in the more left, the green part is the biggest, the man cost and machine cost, and material is only a small part. But so for example, if you take this Print Valley kind of printing, this carousel, then you can improve the productivity by a factor of 3, and you can reduce the throughput of the cost by a factor of 2, because still machining and labor is still an important part of the total cost. If you go on with this, this labor and machining become smaller and smaller, and at a certain moment it doesn't make sense anymore, because really the big part of the pie is material cost. So that you see on the right, then really, yeah, the next step would be to reduce material cost. But still, you went a big step in cost there. Also a really new technology that we see, that is, I'm talking about selective laser sintering, so this laser light is fusing the powder. You also see this fusion jet, so where you have like these black droplets printed across the surface, and with the heat source they're fused. So is that the big future? We saw a research project on the internet that compared the two technologies. That they asked quotes on hubs that used SLS and hubs that used this fusion jet technology. And yeah, surprisingly, the cost was quite the same for low numbers, medium numbers. What was different was the lead time. So with this fusion jet, they could provide the product, I believe, in 4 days instead of 7 days. So a step is made, but not really a really breakthrough in cost at the moment. Yeah, to put it in perspective, we were talking about additive manufacturing. If you look at the total plastic market, that's 290 million tons, so that's a lot. So if you look at the polyamide market, it's 2.85 million tons. If you look at the SLS market, it's just 2,000 tons. So it's really a small market. So, but if recently a big Dutch bank published a report that they foresee a very, very big growth in this additive manufacturing, and of course then it becomes important, because now it's still quite very small, but if you believe these figures of ING, then in 20 years or in 5, it becomes really an important share of this total plastic production. So to come back on this carousel approach, why do we do it? One is that you can put these process stations in parallel. You can also scale it. You can make bigger this carousel, make more process stations. You can even add more processes. For example, now we discussed like recoating, heating, and sintering. You can do inspection. For example, electronics, you can add an additional material. And if you would do that in this traditional way, it would cost you a lot of additional productivity, but because you added more steps in series, and here you can do it in parallel by just making the carousel bigger. So the movie you saw was really a vision in the beginning, but still we also have not animations. I will show you later the generation that is recently finished in an EU project. But the first generation, I think the project was run about 2009. it was more on printing, inkjet printing, and we printed photopolymer that was a UV resin, and later we put wax print heads, but it was not really an additive manufacturing. It was more like putting processes in parallel than making a 3D printer. In the second generation printer, we didn't print, but we moved to selective laser sintering. And so the innovation there, compared to generation 1, was that these build boxes could be moved really individually with different speeds. And another innovation that we put in is normally you have only one laser source. With selective laser sintering, we moved to a laser diode array of the complete width. I will come back on that later. So here you see how these build boxes can move, and everybody says, okay, wow, can your processes keep up with the speed? Up till now not, but of course the build platform should not be the limit, and you can see it can move quite fast. On the right picture, I will come back on that later, is this light engine that we developed, and you see it also on the top. Yeah, so what was the application? It was the Additive project. Maybe some of you know this project. And the application was printing insoles. And you can imagine that for insoles, customization of your product is important. And even you can change the stiffness. As you can see, it is really like a lattice structure. And you can change this lattice structure really to change the stiffness where you need it. Yeah, so to tell a little bit more on this light engine, because that was also a big step. We looked for commercial available laser diodes, and in the end we found an IALDA module. It consisted of 48 spots, and we developed the optics around it and the control. And in the end, we had like 13 of these IALDA modules parallel to each other, covering 13 centimeters of product. So by moving your build box, like the insole in the length direction underneath this light engine, in one go you had the complete sintering. So here you see, if you this build box, it's moving. You see these spots. Each IALDA module gives one spot, because with this demo they are put all on, and in the end you did complete sintering. And what is important here is the speed is not that high, if you can see it. You saw these build boxes going very fast, and this is not going so fast. And important to make it faster is that you have the right power of these laser diodes, and until now this generation we believe it is competitive with the current CO2 approach, but it is not really a big step. And in order to make it a big step, these laser diodes and this light engine has to be improved. I will come back on that later. In the beginning I said there are two parts, like this quality and this cost, and at the moment we're working on the Print Valley 2020, so it's really a new development. I'm the project manager of this project, and we're finalizing the designs. And what the steps here that we make is add more processes. We had these SLS process steps like recoating, preheating, sintering. Now we're adding integrating electronics, so the build box can move to a station where electronics is integrated, and it can do multi-material, so you can have more materials during the printing. And the third step is also inspection, that we do inspection during printing. This is the top view of the system. What you see now, we have a sinter station in it, a recoater, and preheating in the corners. And of course you will need to load, unload build boxes without interrupting the process. You see it on the left below. Maybe I went too fast with, I'm talking about selective laser sintering, but why did we choose selective laser sintering? And we see that if you see service providers making polymer parts, they do a lot with SLS. So, and that's because it is quite high material strength. If you go to PA6, you can handle high temperature materials. Isotropy is good. The material is recyclable. That was also an important one that we got from partners. That is an important topic that with SLA is more tough. And the combine, of course, you can have fused deposition modeling printers with very big, with a very low resolution and build very fast. But with this technology, you have a good combination with resolution and build rate. So in my example, in this animation, I showed 3 build boxes. And actually we do simulations to determine how many build boxes you need for a certain carousel setup. And you can imagine that depends on the process times, how many processes do you have, and these simulations are done like this. For example, you start with 1 build box and you increase the amount up to 12, for example, and look what is happening to the throughput of the system and what is happening to the lead time. And these figures I put in this graph. And so on the horizontal axis you see the amount of build boxes, and on the vertical axis you see the blue one is the lead time, the cycle time, the red one is the throughput. So what you see is if you take 1, it's basically a standalone printer, you have only 1 build box, but if you increase it, you increase your throughput. And the lead time doesn't change that much. But if you make, in this setup, use more than 6 build boxes, then it is really reducing the lead time, because these build boxes are in buffers waiting till it's the right moment for the sinter station, for example. So it's a balance how many build boxes you need. Of course, I'm now talking only on the printing aspect. I already said that there is more to do to come to a final part. And one is, for example, this box is very hot when it comes out. You have to cool it with the right rate. You have to get the powder. In the beginning, all the products are really surrounded by a lot of powder. You have to get rid of it. And of course, you want to recycle this powder. So you have to get it ready for the next job, and you mix it with new powder. So also these steps have to be automated. For the moment we are focusing more on the printing part, but we already have first concept setups also for example, for getting rid of the powder, more automated. So this is on this continuous setup. In order to make this factor 10 in throughput, we see that a step has to be made in this light engine. I showed you already this IALDA module, but it really didn't make this big step in throughput. So there still innovation is needed. And for example, to compare the different possibilities to go to a fast light engine, traditionally they use a CO2 laser with a galvo. So they have one laser spot and they move it very fast across the surface. A very normal solution would be, if you want it faster, take 2 of them, and that is also the solution you see in the market. And typically, like 2 CO2 lasers is very common. But if you look at this line array, that's still new. You don't see that so often. With this IALDA. That is not the big step to make, and we're looking at, and we call it lupus. If we can increase this energy density, it's like the watts per square millimeter, to a level that you really can beat a CO2 laser. And that's not only in performance, you also have to keep track of the cost. And of course, for very high throughputs, it becomes easier because the CO2 approach really scales with the amount of CO2 and galvos you need. But what you maybe typically see with these line arrays is that you go to another wavelength, and CO2 lasers, they have a wavelength of about 10 micrometers that absorbs in polymers very well. These low wavelengths do not absorb, almost not absorb in polymers, so you have to add absorbents. What is an important aspect for this comparison between this line array and this CO2 laser is the fill ratio, and I will explain why this is a really important part. What you see on the left here is a typical build box. They prepare it to stuff as many products in a limited volume as possible, because then you utilize the process as good as possible. But still, when you do that and somebody is really putting a lot of effort in it, the typical fill ratio is between 5 and 10%. So 95 or 90% of the powder doesn't have to be sintered. And with a line array, it's just as easy to sinter all the material as sinter only 5 or 10%. But for the CO2 laser, it makes a lot of difference. I will show that with this graph. So for the CO2 laser, the fill ratio, more fill ratio takes longer sinter times, but higher fill ratios with this line array doesn't matter. You can move it with the same speed, although even when it is 100% filled. But we cannot make a job 100%. Then you make blocks. That's not the goal of AM. So you're stuck to this 5 to 10% for the moment, and you have to really, with this, this as a given, compete with this CO2 approach. Maybe also you can put this fast light engine in a standalone system, or you can put it in a carousel. And what I said, with the standalone system, like a faster light engine gives you faster process speed, but the increase you have is only limited. We put it in this graph, and so the standalone printer, I have to see. The price-performance ratio is not really improving when you have more CO2 lasers in a standalone system. But if you do it in a carousel, you can utilize 100% your expensive light engine, and then it makes a bigger difference in cost reduction. I think I have some time for the quality control. So, to give you an introduction, so what is the attention point for selective laser sintering on quality? And of course, the material properties are important. And the other one is the shape has to be very precise. And we believe that with process control, you can meet these functional material demands and get more accurate products. And so what affects this quality of the part? And if you look at this laser sintering process, of course, the power of the laser speed have a big effect. Of course, another aspect is what I said, this build box is at a certain temperature. So if you change it, it will have an effect on the quality. The powder you use, for example, the powder particle size distribution, it has an effect. Which polymer you use. So these are all wanted inputs. You can design it, and this is the optimum. But if you tuned it to an optimum, still, in reality, it's not always in this optimum. And for example, your laser can deteriorate, your build chamber is not as homogeneous as you would want, the powder is reused, so it is also not the same as at the start. And also the moisture content can change. And so how to measure these quality differences? And we already did some work with making a lot of tensile bars. And there you can measure, for example, the tensile strength. You can measure the Young's modulus, the elongation at break. Of course, even at the current state of technology, it can be a failure that the build just didn't work. Is your part geometry accurate? And is the density correct? And if I have used too much time, please let me know, because...
I check it.
All right. So what we put in this graph is on the horizontal axle the energy input. For example, you can change the laser power, and on the vertical axle you have the tensile strength of this tensile bar that we printed. And what you see, if you have a very low energy input, then the layers just really don't stick to each other. And if you put it really high, then of course you go to an optimum. But why not go to a very high value? I will show you why. So if you put it very low, you see this delamination. So that's not good. But also, if you make it very high, you can see, I think it's upside down. So upside down, you can have like a lot of extra melt of material to your product. So that's also not wanted. So what you would want is to stay on your optimum process window. And now everything is kind of open loop. So you just hope it doesn't shift too much. So I will show you, because we did quite some modeling in this field, and especially we started with metal, because we started with a lot of metal projects. And what we saw there is that for example, this laser power you can control. But what you cannot control, or maybe you can control, is that during your build, that your product heats up. It doesn't have time to cool down. And then also, not intended, your material becomes hotter, and your melt pool is different than when you just started. So you see on the right, if you have these overhangs, for example, with metals, that your product can heat up. What we also found out is that with this scanning of this laser, you have different edge lengths. You can have very short edge lengths, and then the time to go from one side to the other is much shorter than if you have very long edge lengths. And also that makes a difference in the cooling time. And I will show you an example of a simulation. And we actually measured that also with pyrometers, that this really is an effect that you can see. And here you see this overhang on the side. So from the side you see the top one, and here you see it from the top view. If you make a contour with this product, here you have an overhang, here you don't have an overhang, and that will have an effect on the temperature. And at the moment, a lot of these things are not compensated for. They're just one parameter set. Of course, you have some parameter sets, but not to compensate for all these things. To show you some simulation results, I have to acknowledge a lot of projects for that. We did this in a Dutch project. It's PPS Materials Metals for AM. We did it with a lot of partners, and for direct energy deposition, we did it also in the Borealis project. And what you see on the left, we actually built that product. What you see, this triangle, is actually a cone from the side, and we also printed this cone in reality. And it kind of destroyed the wiper blade, because we already predicted it would heat up, although it is perfectly within the design rules. I think you learned the design rules. It was perfect, 45 degrees. But still, we already simulated that it would heat up to 500 degrees. And indeed, it was glowing when we were building it. And also, here you see the right one is a donut from the top, what you can print. And you have long scan lines and short scan lines. And what you see is that these short scan lines become much hotter because it doesn't have time to cool down. And also that we measured with pyrometers, and we saw that it is actually happening. And of course, not everything that is changing is a problem. There is some bandwidth there, you don't see it in the material properties, but you really have to know, is it within a certain boundary, or is it outside the boundary? We also did now, because this was all done for metal, we still have to do the simulations for polymers, but we already did some measurements for polymers, where we used a thermal camera to look at the process during selective laser sintering. So what you see on the left is Yeah, after.
Recently starting.
Yeah, okay. I will wrap up. So what you see here in this movie is that there is a long time you still have this heat of this laser. So it's not like you melt it and then the temperature is gone. So you really have a long history. And so indeed, these simulations could also show that this has an effect for polymers. Maybe the last slide. So in the end, what you want is to compensate for the disturbances. One could be using models, and the other one using sensors, like what I showed. And then we believe that it can have an important effect on better geometry accuracy, better material properties, and also one-time right build. Yeah, I will skip this one. All right, thank you for your attention.
So Edwin must leave us before the end of the seminar. So if someone has some question for him, it's the right time to do that. So do you have some questions? Yes, of course.
The carousel approach.
Yes.
Did you test it for polymers and for powder, for metal powder?
No. We didn't do it for metals. We actually did some metals, but more like polishing, that we scanned it and polished it on another occasion. But we didn't do metal printing yet.
Do you think it can be done with powder?
Yeah. But, for example, like this oxygen content, that's an important one. And you have one level for polymers, and you have a more stringent level for metals. So we have to see how good we are, and then you can decide, okay, metals are in reach.
Question? So I see it's very interesting the part related to the carousel, and so in the end, you think that the best way to connect additive manufacturing process to all the post-processing is to create a new platform which includes both, like an additive manufacturing, is right? Or do you think there could be other methods to do this?
Yeah, this automation part will be a big step, and what you see a lot when you do automation is these long chains. So yeah, our vision is that this can help, and more than making a lot of standalone systems and having a robot arm picking out all the build boxes. But yeah, we'll see in the future. Yeah.
Okay, thank you very much. So.